think we're ready. Basically, Jens must participate in this, and that's why he has a mic. And the way this works is there are lines that you can see on the slide. Every line is read by a different audience member. And I will start, and I will pass the mic to the next audience member, who will say the next line. And we ignore the A, B labels. That's how it works. And Julia does not say anything, apparently. Does that sound good? Everyone understand? You get the microphone, you read the next line. That's it. All right, so we ready to go? A, brightly. This is a talk about summations.
Summations?
Yes, summations. Like the big sigma in discrete mathematics?
Like the big sigma in discrete mathematics?
You mean like the formula $\sum underscore I equal 1 power x fi equal f0 plus f1 plus \c dot plus fx dollar question mark?
Yes.
But it's not a formula.
Beg pardon?
It is the representation of a formula.
In LaTeX. Monsieur Magritte, thanks for coming by.
Oh, Monsieur Magritte, thanks for coming by.
Oh, yes,
Thanks.
Okay, thank you too, and congrats. Great to be here.
You're most welcome.
Quick question, a summation, is it represented with a for loop?
Yes, it is. For example, here is the representation of the sum in NCC. It goes as a return type integer, foo argument type integer x. In sum equals 0, for loop with I equals 0 goes to I less than x, I plus plus, and then sum plus equals f of I, and we return sum. If f is the constant function that returns 1, the result is x plus 1 for any given non-negative x.
Thank you. And this talk is about nested summations?
No, I think it should be you.
Nested summations, yes, like $\sum, I can't read that. I equals 0 to the power of x, \sum, j equals 0 to the power of y, f of I, j, $period. I think the labels don't matter other than the person who read the title.
So they are implemented with nested for loops? No. Int bar, int x, int y, int sum is equal to 0 for I is 0 less than x, I plus plus for I is equal to 0, I less than or equal to y, j plus plus, sum plus is equal to f of ij, return sum.
So for any given non-negative x and y, if f is the constant function and returns 1, the result is x plus 1 times y plus 1.
Beg your pardon?
Well, yes, the result of this inner sum, $, slash sum underscore classes. Well, everyone can read the code. Is that 1? Is 1 added y plus 1 times? So it is y plus 1 for any given non-negative y.
So the result of the outer sum 0 to x, y plus 1, is y plus 1 added x plus 1 times. And so it is x plus 1 times y plus 1. And for any given non-negative x and y, I see.
The inner sum implements addition as iterated incrementation, and the outer sum implements multiplication as iterated addition.
Professor Church, thanks for coming by.
God, I'm getting a block of code. Quick observation, we can nest the summations even more. You are most welcome? No.
Thank you.
Thank you too, and congrats. Great to be here.
You are most welcome.
Quick observation. We can nest the summations even more. Look, $sum underscore I1 equals 0 to the power of x, \sum I2 equals 0 to x, \sum I3 equals 0 to x, 1.
Just a sec. Int BAZ int x int sum equals to 0 for int L I1 equals to 0 and I1 less than or equal to x and I1 plus plus, and the second for loop int I2 equals to 0, I2 less than or equal to x and I2 plus plus, and for third loop int I3 equals to 0, I3 less than or less than or equal to x and I3 plus plus, and the sum plus equal to 1, return sum.
So the result is x plus 1 to the power of 3 for any given non-negative x?
Yes, exponentiation is implemented as iterated multiplication.
Right, nest 3 sums, exponentiate with 3.
And nest 4 sums exponentiated with 4.
So how do we implement $sign and $sign nested sums so that we can compute $, parenthesis x plus 1, right paren to the power of n, $, question mark?
Well, n should be a parameter, just like x.
We implement it with an outer for loop? No, wait, that won't work.
We need a metaphor loop?
Or we could implement the nesting recursively, considering that it is defined inductively.
We could do that too.
Students are hereby drafted. Just read the line. Okay, I think we're going to wrap around. We're going to do modular arithmetic. Is it me now? This code? Oh, my God. Okay, let me try. Int compute e, int x, int n. Curly braces are silent. Comments are silent. If n equals 0, return 1. Else int sum equals 0. For int I equals 0. I is less than or equal to x, I plus plus. Sum plus equals compute e of x, n minus 1. Comments are silent. Return sum.
Yes, I did. So, for any non-negative x and n, we get x plus 1 power n if we nest n summations from 0 to x, with 1 as the body of the inner sum.
And we get x to the power of n if we nest n summations from 1 to x.
Which is not a good idea. For indexing, better start with 0.
Professor Dijkstra, thank you for coming by.
Thank you too, and congrats. Great to be here.
You're most welcome.
Quick question. What if you put decreasing natural numbers as the successive upper bounds?
Let me try. Int compute f, int x. You said that comments are... Sorry.
It's up to you.
X is the upper bound for sum. If x equals 0, return 1. Else it's sum equal 1 for int I equals 0, I less than x, I plus plus, sum plus equal, compute fx minus 1. Recursive call on a decreasing argument, return sum.
Oh, we get x plus 1 factorial, a factorial number for any given non-negative x.
Ah, right. Now we multiply decreasing natural numbers.
So that's the point of the paper?
The point of the paper is to make the upper bound of an inner sum depend on the index of an outer sum.
Can you give a simple example? We only have 20 minutes here.
I think 20-some.
You read that.
The fourth ball. Am I the fourth ball?
Yes, you're the fourth ball.
You're right, only 20 minutes. So here is the simplest example. The outer upper bound is the given x, and each of the inner upper bounds is the current index. Look. Sum of all these things, dot, dot, dot. Slash sum underscore curly brace I. Can someone format this, please? Sum of I1 equals 0 of x. Sum of I2 equals 0, I1. Sum of I3 equals 0 to I2. And so on up to sum of in equals 0 up to in minus 1 of 1.
Okay. Okay. Well, okay.
Okay, and the result is?
It is $C open parens x plus n comma n close parens $, a binomial coefficient.
A binomial coefficient, and you know that how?
Well, we test it first, of course, and then we prove it by induction using the Coq Proof Assistant.
Oh, I see. Do you have another simple example?
I get the easy part. Of course. Of course! Instead of the current I as the upper bound, pick I plus 1.
Let me try. Int compute C, int j, int n, where j is the upper bound of the sum when n greater than 0. If n equals 0, then return 1. Else int sum equals 0 for int I equals 0, I less than or equal to j, I plus plus. Sum plus equal, compute C, I plus 1, n minus 1, and return sum. Oh, thank goodness.
Okay, and the result is?
A Catalan number.
I see.
And here is what the paper is really about. Picking $1 minus I as the upper bound.
Why not?
Let me try. Int compute f int I int n. If n equals 0, return 1. Else int sum equals 0. For int I equals 0, I less than j, I plus plus. Sum is plus equal. Compute f 1 minus I n minus 1. Semicolon. Return sum. Semicolon.
And the result is?
A Fibonacci number. A Fibonacci number, and you know that how?
Same. Testing and then proving. The whole paper is formalizing.
By the way, these nested sums, where do they come from?
Mosner's theorem.
Mosner's theorem.
It's a really cool construction of streams of successive powers in their book of numbers.
Oh, sorry, I can't read it from you.
But there are no streams here, just sums.
Right. As it happens, Mazur's theorem hinges on dynamic programming, where streams contain intermediate results that are computed only once. Remove dynamic programming, you get nested sums. It's good fun.
So the paper is about Fibonacci numbers as nested summations.
Got an easier one this time. You want to try it? Okay, I guess we'll do modular arithmetic again, resetting. So the paper is about Fibonacci numbers as nested summations. Question mark?
Where are we? Oh, yes. Yes, and Fibonacci-like numbers, such as Lucas numbers, which start with 2 instead of starting with 0.
I see that they are also Jacobstahl numbers.
Yes, and Jacobstahl-Lucas numbers too, which start with 2 instead of starting with 0.
What a lot of induction proofs. Hey, big ones too.
Time out, guys.
Ouch, I'm broken.
Okay, so to sum up.
Time out, time out. You can't add anything.